All right, welcome to page two, and what we're going to talk about in on page two is just how to parameterize the certain functions that we're dealing with. So, say if we substituted t is equal to sine u in example one, so instead of saying t, we said sine u. What would our answer be? Well, we would still get our answer of 7/3, because all we're doing is we're kind of just doing like a u substitution. We're changing what t is, but even though we change, the value of t, we also have to change our integral from where we're going from, and then we're still going to use sine of u for that, and so therefore we're still going to get the same distance under our curve. So or not under, but the same distance on our curve. These two equations are parametrizations of the same curve C. No matter which equation we use to compute the length of C, we will get the same answer. So, a definition, suppose that C is on a curve given by a vector function, and RT is equal to f of ti, g of tj, plus h of tk from a to b, where r prime is continuous and C is traversed exactly once as t increases from a to b. So we define its arc length function s by s of t is equal to just the integral from a to t of the magnitude of r prime of u du. And so basically what we're doing is, instead of, saying we're going from 0 to 5 or 0 to 2 or whatever, what we're doing is we're taking, our vector function, and we're trying to find the arc length from some value to t. And so what we're going to do is, because we're going from some value to t, this is a way that we can find the arc length on any part of our curve just by putting things in terms of arc length. So if we differentiate both sides of this equation, we obtain ds over dt is equal to the magnitude of r prime of t. So it is often useful to parameterize a curve with respect to arc length, because arc length arises naturally from the shape of the curve and does not depend on a particular coordinate system. So one really good thing about putting things in terms of arc length is it makes our function, easier to deal with. Some, not always, but it would make it easier to deal with. And so in order to parameterize our function, what we're going to do is just basically use our formula s of t, which gives us the arc length. So s is what we're going to say for arc length. And then what we'll do is we'll substitute in for our function, instead of saying t as our variable, we're going to substitute in a dummy variable u, and we're going to go from integral from some starting point a to t. All right, so let's go ahead and see what that looks like. And so what we want to do is we parameterize the helix r of t is equal to cosine ti plus sine tj plus ck with respect to our arc length measured from 1, 0, 0 in the direction of increasing t. So we're going from a certain point. So this point that we're going from has, gives us a starting value for t. So we need to figure out, okay, well, where are we starting? Well, if r of t is cosine t, sine t, and t, what value for t would allow us to start at this point? And that would be t would have to equal 0, because cosine of 0 gives us 1, sine 0 gives us 0, and t, if it's 0, gives us 0. So we know that t is equal to 0. So there's our starting point, because we're going from 1, 0, 0. So now what we want to do, we want to go ahead and find out, what's our derivative. And so our derivative is going to be r prime of t is equal to derivative of cosine is going to be negative sine of t I plus cosine t j, derivative of sine t is cosine t, plus k. All right, and now let's go ahead and do our ds over dt is equal to, now if we did r prime of 0, because that's where we're starting at, what we're going to get is negative sine t, which gives us 0 I plus cosine 0, which is just 1, so it gives us j plus k. So really, r prime of 0 is just j k. Alright, now, if we're doing r prime of t, that's going to head and give us, here, I'll do the work underneath it, the square root of negative sine t squared plus cosine t squared plus 1. And we're going to be given sine squared t plus cosine squared t plus 1, which is just the square root of sine squared t plus cosine squared t is just 1. So 1 plus 1, which is going to give us square root of 2. Alright. So now, when I put things in terms of arc length, I can go ahead and just substitute in for the magnitude of r prime. So s is equal to s of t. So in this case, our starting point is going to be 0, and we're going to t, and now we're going to substitute in our w variable, r prime of u du. Now, from above, we know that r prime of u is just going to be square root of 2. So then we can say, well, now we have the integral from 0 to t square root of 2 du. We'll go ahead and take the derivative, and so, the integral of that, and so we're left with the square root of 2 t, square root of 2 u from t to 0, and we're just going to be left with the square root of 2 t. So now we know that our arc length is equal to the square root of 2t, and so therefore, if s is equal to square root of 2t, that means that our t is equal to our arc length divided by the square root of 2. You write that 2 better. And so now we have this new variable for t, or a new way of writing t, as in s divided by square root of 2. So now we have, we parameterize our function. So instead of saying r of t, we're going to say r of t of s, which is just going to be cosine. Let me go back to cosine. It says saying cosine t, cosine s over square root of 2 I plus sine s over square root of 2 j plus s over square root of 2 k. And now we've written our vector function in terms of our arc length.